Okay, Bismillahirrahmanirrahim. So we continue with this second video. So last time I cover until example 2. Okay, it is a very straightforward example. Then you just apply the equation to find the solution. So example 3 I want to cover because it's a bit new for you. Okay, to determine the shear stress. Okay, shear stress only for this equation because it's depending on the radius. Okay, radius of A and radius of B. Okay, so but before that we have to understand on how to determine the internal load. Okay, so you have a many external load in the system, but depending on the question, where is the location? So you have to determine the internal load at that particular location. Okay, example 3. So the shaft is supported by two bearings, is subjected to 3 torques. Okay, we have a 3 torques, 4,250, and then 3,000 and 1,250. And the question is, determine the shear stress developed at point A and B, located at a section AA of the shaft. So this is the thing that we have to find, where is the exact location, okay, to find the shear stress of tau. Okay, it's not tau maximum as illustrated in example 1. Okay, the question asking you to find the shear stress. It can be a maximum shear or it can be a normal shear. Okay, so once you have this one, the first thing that you need to do is to find the internal load at that particular cross-sectional area. So we have a AA area there as illustrated in the second figure here. And the the C for the A position is given there, 75 millimeter. Radius for the second one from 0 to B is 50 millimeter. So you have to develop tau, okay, at this particular location. So let me draw the tau, for example, here. Tau maximum. Why I put maximum? Because A is the maximum radius. Okay. So B is tau B lah. Not tau maximum. This can become tau A as well, or tau maximum. Okay, so how to do? The simple one, you have to maybe jot down or write every single equation that you know. For example, tau is equal to TC over J. Okay, TC over J. This one is tau maximum lah. So C is given, which is a 75 millimeter. Okay, and then T is unknown. So you should get it from the internal loop. Okay. J can be calculated using the inertia polar moment. Okay, polar moment of inertia, J. Okay, since this is solid, J will be J pi over 2 R power 4. Okay, ROC lah. So as stated in the previous slide here, ROC power 4 over 2. Okay, so once you have the either, then the first thing is to draw FBD. So draw FBD at the desired part. So this is the middle part that you have to cut and then you split into two. Okay, so AA is the middle part or cutting section. So you cut at AA, so will be split into two, left and right. So as I mentioned, choose the best or the simplest free body diagram. Okay, in this case, we choose left lah. It doesn't matter if you want to choose right. The answer will be similar. Okay, the answer will be similar. I will show you. Okay, let's say in this example, showing you we choose the left part. You cut at AA and then you split it. You draw the left part only. Okay, so left part we have 4 torques, 4,250 and also 3,000. Okay, so once you cut it, so we can imagine that there is an internal load. So basically, as I mentioned in the class, basically if you have internal load where we have 4 internal load, as a load, normal load, sorry, shear load, okay, and then torsional and bending. Okay, in this case, because the external load is only torsional load, so the internal load for this particular AA position having the torsion load only. Okay, by right we have normal, okay, shear V, and also the bending. Okay, but all of them are zero, zero, zero. So I always repeat this one, so to make sure that you understand. Okay, that's why we just eliminate those three lah in the FBD. But later on in chapter 8, you will learn about the combined load. So combined load having 4 loads lah later on, 4 internal loads. So we will go through later on in the chapter 4, chapter 8. Yeah, I erase this one. Okay. All right, so once you have the FBD, so the FBD for the left part, okay, and then you have to calculate the T. So you assume T is rotating this way, or I call it clockwise lah. Okay, I call it clockwise. So using the equilibrium of equation of equilibrium, sorry, okay, you have to find the unknown of T, okay, using this formula. So moment, okay, because the x-axis is only 1 equal to 0, so let's say anti-clockwise for this one, okay, is positive. Okay, so you will have 4.25 k. Okay, I just put k, not unit. Okay, in the calculation here they put unit, but I suggest you to put only the value. But in the end of the day, the final answer should be including with the unit lah. Okay, 4.25k. Okay, and the next one is 3,000, which is oppose the assumption, this assumption. Okay, and should be negative 3k lah. And also T, T is our assumption T, which is opposed to position, oppose the assumption. So must be equal to 0 as similar like below. And then you rearrange, then you will get T equal to 1.25 kilonewton meter. Okay, if FBD is on left side. So let's say you are taking FBD right side, the answer will be same. Okay, so the answer will be same. So sorry, I draw it here. So you take in here, for example, right side. So this one is 1.25k. Okay, this is the load. So you have this position or direction of T. So using equilibrium system, T minus 1.25k equal to 0, T equal to 1.25k Newton meter. Similar. Okay, this is the FBD for right. Okay. It's up to you. It's up to you. So as I mentioned, always you have to choose the best and simplest one. Okay. Once you have the T, then you can put the T into the equation, Tc over J. So you can calculate individually, calculate J first. Okay. If J, okay, this is the thing that you have to understand. Some people, some student putting different value of C into the J equation. Okay, this normally happen in the previous student. So the J equal to pi over 2 C power of 4. Okay, C power of 4. So C is the maximum radius. Okay, sometimes student putting the radius of 15 millimeter here. Okay, 15 millimeter. They put 15, they put pi over 2, 0.015. This one is wrong. Okay, so C is the longest radius, the maximum radius, which is happen in this question is 75 millimeter lah. So that's why we have 0.075 meter. Okay, and then you put into the equation, and then you will get the J. It is better to calculate manually. I mean individually, sorry. Okay, step by step. Okay, step by step. You calculate the T, you calculate the J. Once you get J, you substitute J into the equation of T of equal to TC over J, and then you get it. because based on my experience, a student is not following the sequence, so it is difficult for me to find the correct answer. I will be taking more time to find the answer, so it is better to calculate individually and follow the sequence. Okay, don't jump into different sequence lah. Okay, back to this one. So there are two questions. There are two shearing stress that you have to find. The first one is now for A. So you have T, you have G, you have C. So just substitute T, 1.25, okay. C is equal to 0.075, okay. And then the J is 4.97 times 10 power of negative 5. So again, I remind you to convert all the value into SI units. Okay. So Newton meter, meter, and also meter. Okay, don't put millimeter anymore. Don't put micrometer and so on. Okay, just put SI unit. And then once you have this value, then you convert into MPa. Normally we give the answer in MPa, megapascal or Pascal it is. Pascal is the SI unit as well. Doesn't matter. Okay, so this is the answer for tau A. For the tau B, so the tau B, the only difference is the R. So just putting the 15 millimeter, 0.015 meter into the equation, you will get the final answer of the tau B. Okay, so if you can summary here, you can see the maximum is happen to A lah, of course, because the radius is highest. So the maximum tau for A is 1.89 compared to B 0.377 megapascal. So if you go back to the previous slide, so I go back to the previous slide. Okay, it is parallel. You have to understand the solution and also the statement that we have discussed in the previous slide. Oh, sorry. Macam mana ni? Okay, let me go again. Okay, so you got two different answers. So this is the thing that you have to remember. The distribution of the stress is not known, okay? And the other one is, sorry, the last one is the distribution of the shear and stress due to torsion cannot be assumed uniform. So it's not similar like axial load. So every single point having a same value of stress, but the torsional load having different value of stress for each location. Okay, so you have to remind because it is depending on the radius. So T is depending on the radius. Tau is depending on the radius. Okay, wait, I go back to the example. Okay, so not yet finished. I will explain about the distribution here. So once you have 1.89 megapascal, this one is typo, should be P in capital letter. Okay, megapascal. So you can illustrate or you can draw the distribution of the stress like this figure. Okay, so since it's rotation, okay, so the direction should be in rotation like this way. So rotation like this one, for example, T. Because the previous one we got T, this direction. Okay, this direction. Okay, this direction I highlight again. So the direction of the shearing should be following the direction of the torsion. Okay, it's similar like axial load lah, axial load. So the direction of axial load is this way, for example. Okay, and then the direction of the shearing, the stress should be same as the direction of the internal load. So this is the stress. Okay, so similar. I believe that it is same all for all loads. Okay, so this should be understandable by you. In the final exam, we ask you to draw like this one. So make sure that you draw the correct direction and also the value lah. Okay, for the B, okay, 0.377 megapascal. Here, the value is 0.377 megapascal, and the direction should be towards downward. Okay, should be downwards. Okay, downwards. Okay, because it's the rotation. Okay, rotation. Okay, so basically in the final exam, any engineering reports, if in industry later on, you have to draw this stress distribution figures. Okay, to more understand, to prepare report and so on. Okay, so I will now cover example 4. The answer is given. Also, example 5, the answer is given. You can try by yourself together with your friend. Okay, the answer is given for example 6. So I will start to cover, sorry. I will start cover the next subtopic, which is angle of twist in elastic range. So basically, angle of twist is a strain. Okay, is strain, shearing strain. For this case, a shearing strain. Okay, for axial load, it's called a normal strain. Normal strain is not angle, it's a length or deformation in length or changes in length. Okay, but shearing, because the angle is involved, so we have to calculate the angle. So the angle is shearing strain. Okay, this one is shearing. The other name is, sorry. The other name is a shearing strain. Okay. Last slide is shearing stress. Okay. This time around is shearing strain. Okay, so this slide is actually, I think, it's not, I cannot say that it's not important, but it is important for you to understand how we generate or how we develop the equation, the final equation. Okay, because the mathematician or the physician or the scientist develop the equation from the scratch, from the general assumption, okay, theory, and then somehow they get the final equation, and we just use the final equation. But before we use the final equation, we have to understand where is the final equation coming from. Okay, so even though it's not included in the final exam, but as an engineer, you have to understand the root equation. We call it root equation. Okay, for this one, how the scientists generate. So we go through one by one. Okay, recall the angle of twist and maximum shear strain are related. So again, if you still remember in robust shape in the previous slide, okay, so we have this equation. So let me repeat. So rhombus, so we have theta here, we have phi here, right? And also this is a length, this is a c. Okay, so using the mathematical equation or the ratio, okay, you will have phi over c, okay, equal to theta over L. This is the ratio. So in mathematics, I think I have explained it in the previous slide, previous class as well. Okay, once you have this one, so you rearrange to get phi only. So phi maximum in this case is maximum is equal to c theta over L. Okay, and the next one in elastic range, the shearing stress and the shear are related by Hooke's law. So I've mentioned before, so Hooke's law, there are many equations. For example, F equal to Kx. Okay. For example, sigma equal to E epsilon. Sorry, epsilon E. Okay. Another example is tau equal to phi g. So this is the Hooke's law. So using the Hooke's law of the tau equal to phi g, you will get this formula. Okay. So let me write the formula first. I will explain to you. Okay, since you have phi equal to tau over g, so phi equal to tau over g, right? And then tau can be replaced with TC over J. So TC over J is from the previous slide. TC over J here. So you insert tau into the equation. In the end of the day, you will have TC over JG. Okay, TC over JG. Okay, the idea is that we want to find, again, the idea is that we want to find the equation of phi. Phi is the angle of twist lah. Okay, the angle of twist. Okay. So once we have the phi equal to TC over JG, okay, this one is phi. Phi is located at the longitudinal direction, okay, which is here. This is the phi, okay. But the angle of twist is located at the cross-sectional area. So you have to differentiate between these two. So we are not going to use phi equation in our calculation because phi is located at the longitudinal. Angle of twist is located at the cross-section area, which is theta here. So you have to substitute theta. Theta will be equal to TL over JG lah. Okay. So instead of TC over JG, C you substitute with L. Phi substitute with theta. So at the end of the day, you will get theta equal to TL over JJ. Okay, so this is the equation of the angle of twist or shearing strain. Okay, so normally you have to understand those two terminologies. So angle of twist, similar like shearing strain. So sometimes we ask angle of twist, sometimes we ask shearing strain. So it will be tricky for you lah. Okay. All right. So the next statement, if the torsional loading of shaft cross section changes along the length, the angle of rotation is found as the sum of segment rotation. Okay. So theta equal to TL over JG, where we can use this formula for a single segment, like in the first figure of the top left. Okay. So let's say we have the second figure at the bottom left here. Okay. You need to sum up everything. Okay. So for example, here you have 3 sections. I put in different color. Let me change the color first. Okay, segment 1, segment 2, I make it same EDC because the length is similar, the cross-sectional area is similar. Okay, and segment 3. Okay, once you have 3 different segments, you have to sum up every single segment into the equation. So that's why we have this equation of the theta. Okay, theta equal the summation TL over JG. So in this case, in the example, we have T1 L1 JG1, okay, plus T2 L2 J2 L2 JG2 plus T3 L3 J3 J3 G3. Okay, so when you have the different length, different cross section, so you cannot make it all together in one equation. So you have to sum up every single part. So this thing that happen when you have a different section, different segments. Okay, but in the end of the day, you have only to remember TL over JG lah. JG. Or the best thing is that remember the root equation. Okay, the root equation for the shearing stress is tau equal to TC over JG is TC over J. The root equation for the shearing strain or angle of twist is theta equal to TL over JG. Okay. Okay, sign convention. Sign convention is also important for you. If you are wrongly assume the convention or the direction, you will get the wrong answer. Okay, so this sign convention, if let's say you have the cylinder rod like this one, okay, your thumb finger should be pointing upward. Okay, uh, let me find something to show. Okay, let's say this is the rod. So your thumb finger should be pointing upward, and your other four fingers in indicating the torsional rotation direction. Okay, as mentioned, as shown in this figure. So the thumb, okay, the thumb here should be upward, sorry, upward. Okay, and this four fingers is indicating the direction of torsional. Okay. Okay, if let's say you follow this one, okay, so it will be assumed positive for all. Okay, T is positive, okay, because it's following the assumption, the sign convention. Okay, I'm giving you an example where we have a negative value. This one is positive, positive T lah. Okay. Okay, I'm giving you an example where the T is negative. So we have a rod, okay, and then the direction. Let me change the color, and the direction. Oh, sorry, and the direction is this way around. Okay, so in the T direction. So if you follow this one, your thumb will be inwards. Okay, I draw the thumb, and this is the other finger. Okay, so other finger should be following the direction of torsional. The thumb will be automatically either inward or outwards. Okay, so in this case, the thumb is inward. So means that if this case happen, the sign conversion over T is negative. Okay, so you have to remember this one. So we will go through later on in the example. I think you can more understand about the sign convention later on. If you are wrongly set the sign convention, the answer will be different and wrong. Okay. So the below one, the below figure, the same example lah. So if the thumb is pointing upward, the T is positive. Same goes this one. Okay, the thumb is pointing upward, the T is positive here. Okay, let's read the statement here. Sign convention for the internal torque and the angle of twist of one end of the shaft with respect to the other end. Okay, so sign convention of the internal torque indicating the angle of twist. Okay, use right hand rule. Okay, don't use left. Use right. Okay, both torque and angle will be positive. So if you follow the thumb is upward, both torque and angle is positive. If the other way around, will be negative as I'm shown. Provided the thumb is directed upward from the shaft when the finger curl to give the tendency of rotation. Okay, so I already explained, okay, in the figure. Okay, this example, simple example, you have a number of external forces of torque, of torsional. Okay, there are four torques. Okay, and then you have to determine the sign convention. So basically, if you want to do this one, it's depending on the question. Let's say we are trying to find the angle of twist. So angle of twist, again, theta equal to TL over JD. Okay. So the thing is that T should be positive or negative. L will be scalar product, J is scalar product, G is scalar product. Okay. T is the dot product. So the dot product having direction and also value lah. Okay, L only value, J only value, G only value, no direction. So the direction indicating for the T only. Okay, so for this case, let's say you separate it into 3 FBD. So the first one, the second one, the third one. First, second, and third. When you cut at the specific area, you will have the FBD lah, left or right part as usual. Okay. From the FBD, you will determine the top, in this case, internal load. Okay. So we go to the next one. So if you cut it here, number one, you will have a left part. So we get it left part, and then the internal load is TAB, okay, which is the top load, and we will get the value straight away because it's a simple FBD. So TAB equal to 80 Newton meter, and the direction should be using right hand rule, and the sign conversion of T should be following the right hand rule. So in this case, okay, the finger, your forefinger, okay, will be like this one, and your thumb finger will be like this one, okay. Right. So the forefinger indicating the direction of torsion. Okay, so it will be rotated like this one. So if let's say this one, okay, positive, means that the TAB is positive lah. Okay. Or okay. Alright. This one is straightforward. Okay, we go to number 2. Okay, we go to number 2. You cut it at the center. You take the left part for your FBD. So left part, we have external load of 80 and also 150 lah. 80 and 150. So TBC. Okay, this is the thing that normally student confusing on how to determine the internal load direction. So let me show you. So again, for one, you have to understand you have to apply the Newton's law. Okay, so when you have an action, you have a reaction at the other side. So for this one is action. The other side is reaction. The reaction should be opposite direction lah. Okay. Same goes to this one. This is the action. You have to take the nearest one. This is the action. This one is a reaction. This is action. Sorry, this one is a reaction. This one is action. Okay. So I want to highlight this because many students do not know how to put the direction. Okay, so the direction should be considering the third Newton's law and also take into account of the nearest external load. Okay, so number one settled. We go number 2. So number 2. So number 2, we will apply the equilibrium system to get the TBC. Okay, this one is just straightforward to get the TBC using moment equal to 0 lah. Okay, so in the end of the day, if you're using moment equal to 0, you will get TBC 70 Newton meter. Okay, that one is value. How about the sign conversion? So sign conversion, you have again to use a right hand rule. Okay, so from here, let me delete a bit. Okay, let me delete a bit. Okay, from here, you can get the forefinger like this way. Sorry, my drawing is bad. This thumb, this is your forefinger. Okay, so forefinger must follow the direction of the reaction. So the thumb is pointing inward. So if the thumb is pointing inward, means that the TBC is negative. Okay, as simple as that. Okay, we go to the number 3. So you cut at CD, but in this case, we choose right side. Okay. Okay, we have action, which is 10 Newton meter. Okay. And then the other way around is reaction, which is TCB is unknown. So using the equilibrium system of moment equal to 0, you will get TCD 10 Newton meter. But this one is only indicating the values. For the sign conversion, again, you have to use a right hand rule. So it is similar like number 2. So the thumb is pointing inward. Oh, sorry, my my drawing is bad. You have to apply a right hand rule, so your finger will be like this one, okay? Your body like this one, your finger like this one. So the finger is the thumb finger is pointing inward, and your other four is rotating like this one. So if this case happen where your thumb is pointing inward, so the TCD will become negative 10 newton-meter. Okay, that's why we have this value. Okay, TAB positive, TBC is negative, TCD is negative. Okay, if you want to calculate the angle of twist, this is the way that you have to put the value: positive, negative, negative, and the L is depending on the segment. Okay, so LAB what, LBC is what, LCD is what, and JG, since the cross sectional area is same and G is also same, then you can put the same value for each segment. Okay, this is the idea. Alright, I think I stop here for the second part of the video. I will continue the next one for covering the example. Okay, see you next video.